Hello, participant. Welcome to the next part of our sessions that is related to testing of hypothesis. Remember, earlier we did with two groups testing of hypothesis where we have used t-test. After that, we have k-independent sample test, right? Where we have done analysis of variance one-way ANOVA, right? Which was primarily related to the parametric part of the k-related, means where the values of k is more than 2, means more than 2 groups are there and these groups are independent. So as we have mentioned that we have used a word that was one-way ANOVA. So we are moving forward with the other concept that is known as two-way ANOVA. So as you remember the case that we are following here, that was the Ventura, right? In the Ventura, remember, we are analyzing the sales and we have analyzed the sale in ANOVA with respect to the 4 locations, right? So uh, we have classified the sale uh, as per only one independent variable, that was location. But there was one more, um, that is a type of the outlet, whether the outlet is a rural outlet or the urban outlet. Suppose we want to examine the combined effect of these two factors. One is the location and other one is um, the type of outlet or the rural urban. Then we have two factors and accordingly we will be going for analysis of variance or ANOVA two-way. So here I am sharing my PPT so that we will be discussing that concept. Right? So just to connect with the case, right, we have examined earlier that since we were examining the sales of the outlets. Remember, earlier when we were doing one-way ANOVA, we have analyzed sales of the outlet with respect to the third quarter. So we are continuing with that. So in that case, we have examined with respect to one factor, and the first factor was location, where we have taken northern, eastern, western, and southern location. Suppose along with this, we want to consider one more factor, that is type of the outlet. Okay. And remember that in the type of the outlet, we have two type of outlets, rural as well as urban. So the another factor is type of outlet, whether we are going with the urban outlets or we are going for the rural outlet. Right? So here, if we want to examine the impact of these two factors on this dependent variable. So this concept is known as two-way, because there are two factors, two-way analysis of variance or two-way ANOVA. Right? If we consider this part in the form of relationship, so here the dependent variable or y was sales, which is a metric quantity. And in one-way ANOVA, when we have one-way ANOVA, then in that case, the independent variable was location. And as we remember that this location is categorical or non-metric. Right? So in that way, one-way ANOVA can be termed as a study of the relationship where we have two variables. One is the dependent variable, which is metric in nature, and other one is the independent variable that is non-metric in nature. If we go with further to two-way ANOVA, in two-way ANOVA, we have two independent variables. They are x1 and x2. They are locations and the other one was type. And remember, both categorical, both are non-metric. Right? So in that way, two-way ANOVA can be supposed to be a study of relationship where the dependent variables remain metric and independent variables are two, both are non-metric or categorical. So this is one way to examine this. Now, here we are going to examine the impact of these two factors. Let these two factors can be termed as A and B. Here A is location, which has four levels: 1, 2, 3, 4, or north, east, west. And B is the type, which has two levels. Okay. Now, so independently, we are going to examine the main effect of A, main effect of B. And after that, we also consider the interaction effect of A and B. Right? This is known as interaction effect. Now, why we study the interaction effect? That it is that the interaction effect that is denoted by AB. This is the interaction effect. This interaction effect is not necessarily equals to the individual effect of A and B. These are the main effects of A and B. Like even in the medical field, sometimes the two drugs given independently might not have the desired impact. But if two things are given side by side or two things are given simultaneously, right, then their impact would be different as the individual impact of these two. This impact can be positive and this impact can be negative. So here actually we are examining three terms. One is the main effect of A. A is the first factor. The second one is the main effect of B. And the next one is the interaction effect of A and B. Okay, this we are going to study here. Right? So let us formalize this. Here we examine the effect of two assignable causes, right? Like here, the two assignable causes in this example is location and the other one is the time. And different categories of these two factors. Remember, the location have four categories and the type has two categories. On the response variable, that is the y is the sales. Assumptions remains the same as well as that was ANOVA. Remember, what are the assumptions of ANOVA? Number one, the population from where samples are being drawn follow normal distribution. The second is samples has been selected randomly and independently, and each group have common variance or homozygosity. Okay? So the assumptions, the first assumption is related to normality of the population. The second assumption related to independence of selection, right? And the third assumption related to homozygosity or common variance. They have common or same variance. And accordingly, we have hypothesis that is alpha 1, alpha 2 equals to alpha n, that is equal to 0, means no effect of A, right? Where alpha is the difference of mu I and mu, right? This is no effect of B, and these are the interaction effects. These are the hypotheses. Here we are going to bifurcate it. Now, as we have discussed in one-way ANOVA, remember in one-way ANOVA, we divide or we classify, we bifurcate total sum of square into two parts. One is the sum of square because of A, or between sum of square plus sum of square because of error, or within sum of square. Here we have divided, or we divide, or we classify total sum of square into two parts, into the four parts actually. One is because of A. This is sum of square due to A. This is sum of square due to B. This is sum of square due to interaction, and that is the error, right? So the explained variation here constituted of these three parts. One because of one factor, other because of the other factor. The third one is due to interaction, and that is the residual or error. And as we know, that mean sum of square is always sum of squares divided by degrees of freedom. So here we are having degrees of freedom, right? That is m minus 1. Since A has m category, this is divided by m minus 1. B is n minus 1 because it has n category. And m minus 1 into n minus 1 is the degrees of freedom for the interaction effect. And the remaining one is for the error term. And accordingly, we perform the test for A through the F statistics, perform the test for B for checking the significance through the F statistics, and finally we perform the test for the interaction effect. Okay? So if we want to make the ANOVA table here, so how we can express the ANOVA table? So here we are examining two-way ANOVA. And here we are constructing the ANOVA table. Here, accordingly, the first column would be the sources of variation. Here we have sources of variation is due to A, due to factor A. The other one is due to factor B. The next one is due to interaction effect AB. And the next one is due to error. Error means the extraneous term. And finally, we have total variation. Okay. So we are actually bifurcating, we are dividing total variation into these four parts. And accordingly, we have degrees of freedom. Degrees of freedom can be m minus 1 because there are m levels of A, and 1 degree of freedom is being sacrificed. So to satisfy the condition that summation of xi dot bar minus x double dot bar means deviation from the mean is 0. This is n minus 1. This is m minus 1 into n minus 1. And these are the total number of observation, that is mn minus 1. And this is the difference, right? That is mn into p minus 1. Okay. After that, we have sum of squares. Sum of squares. The total sum of square is being classified, is being divided into sum of square because of A. Next one is sum of square because of B. Sum of square because of the interaction effect AB. Then we have sum of square due to error. And after that, we have mean sum of square. This is mean sum of square, which is simply the division of sum of square with respect to degrees of freedom. So this is MSA. MSA is SSA divided by degrees of freedom, that is M minus 1. Next one is MSB. It is SSB divided by n minus 1. Next is MSAB, mean sum of square because of the interaction. This is SSAB divided by m minus 1 into n minus 1. Then we have MSE, mean sum of square. This is SSE divided by the corresponding degrees of freedom. Right? Remember, we have all these terms here. Right? Okay. Right? And then we have the variance ratio. The first one is FA, right, where we examine the variance ratio of MSA with respect to MSE. The next one is with respect to B, where we examine the significance of the impact of the other factor, that is B. This is MSB upon MSC. Then we examine F of AB, that is MSAB divided by MSC. And accordingly, we examine whether A has a significant impact, whether B has significant impact where, and the last one is whether the interaction has significant impact. Now we are going to do this on SPSS with the same case. Then we will revisit and okay. And these are the slides that you can follow. Right? Just a moment. So here, this is ANOVA. How means this two-way ANOVA is available under general linear model, and we are considering the univariate. As we move forward, we have uh, here we have classification, or where we examine the effect of two assignable causes. We can go for more than two also. So accordingly, we have the different tools. Anyway, this is available under general linear model. So these are the uh, SPSS window sheets, right, that will be helpful for you. So to reach the point where you have this test. So now I'm going for the data analysis using SPSS. So this is the data set that we are using. Again, we are concentrating on a particular quarter sale, that is Q3 sale. You can replicate this for Q1, Q2, and Q4 also. Right? So as we know, all the analytical tools are available under Analyze. So we go to Analyze. Remember, this one-way ANOVA was available in the compare mean, but this is available under general linear model. So our path would be Analyze. Then we go to general linear model. Then we go to univariate. Here, our dependent variable is the sale of the outlets in the third quarter. And then we have these two, that is the location and type of outlet as the fixed factor, and we don't have any random factor. Okay. And after that, we go to the option. In the option, we have some routine one like descriptive statistics, right? We have estimate of the effect side that I will be explaining. The next one is the observed power, right? These are the functions that we are going to use this. Okay. And if we want the post hoc analysis, we can have the post hoc analysis, right? We have the post hoc analysis for both. Okay. Um, we can have for the type also, but here I am not taking because type have only two factors. So that is does not require the post hoc analysis, right? So here we have one. We can have one from equal variance and one from unequal variance can also be taken, right? Okay, and if you want, you can include the type also, but that is not that much required. Okay, and then we continue, and then we press OK. So this is the output that we are going to discuss here. Right? As I have mentioned, that post of test is has not been performed from the types of the outlet because there are less than three groups. There are only two groups. So for that, it is not required. So even if you haven't included that, there won't be any issue, right? As we have discussed, right, earlier also. So here we are the four location. 11 units are there for the northern, 21 units are there for the eastern, 23 cases are there for the western, and 5 cases are for the southern. There are 37 urban outlets and there are 23 rural outlets. These are the uh, two assignable causes that we are going to use. Then we have descriptive statistics that we are going to discuss later on. Now here we will be discussing test of between subject effect, right? So here, as we have discussed, these are the different type of variations. Sum of squares are there, like location, type. This is the interaction effect. Then we error. Then we have total, right? Okay. So if we consider first, we should uh, right. So first, we should examine the impact of the location. As you see, the location is having a p-value less than 0.05. This is less than 0.05, so it is significant. In the same way, this type is also having a p-value of 0.037. This is also significant. But if we consider the interaction effect, this interaction effect is insignificant, right? So here interaction effect is not making any contribution, right? So now if we write all these results on our sheet, so let me, right? You can have photograph of this so that you will be having a connection with what I am going to explain on the whiteboard. Just a moment. So here, as we see that for the first factor, what is the, for the first factor, that is location. Remember what was the hypothesis? That there is no significant difference or impact among the levels of the first category. So here, for the location, the p-value or the significance is 0.000, which is less than 0.05. So we reject H naught at 5% level of significance. Right? So there is a significant impact of the first factor. Then we go for the second factor, that is type, with the same type of hypothesis. Here the p-value or the significance is 0.037, which is less than 0.05. So we reject H naught at 5%. This impact is also significant. So individually, the main effect of the location, there is a significant difference, and main effect of the type is significant. Right? And for the interaction, is A into B, that is location into type. We have the p-value of the significance as 0.724 means we do not reject H0. Or you can say this is H01, H02, and this is H03, right? Remember, we have three hypotheses, H01 for the main effect of factor A, H02 for the main effect of factor B, and H03 for the interaction effect. So you can say that main effects are present. This is present here. The main effect of type, this is also present. And here, the interaction effect of location into type, this is not present as per the hypothesis. So here, interaction effect is not making any sense. Right? Now, here we have some other outputs also. One is the partial eta square. I will be showing you that also. This is partial eta square. Okay? This is actually the effect size, which provides us the percentage of explained variation. Remember, in the uh, when we discuss the partitioning of sum of square, we have SSA, sum of square because of A. Then we have SSB, sum of square due to factor B. The next one is SSE due to the, SSAB. And the last one was SSE, that is the unexplained part. So these three are known as explained variation. And this is known as error or the residual or unexplained. Right? So it provides us the effect size percentage of the explained variation. Higher the value, higher is the contribution. We have one more term. That was the observed power. As we know, in the testing, we have two errors. The one is type 1 error, which is actually related to rejecting H naught when H naught is true. Means falsely rejecting a good hypothesis. And the other one is type 2 error, that is accepting H naught when H naught is false. Okay, means falsely rejecting a wrong hypothesis, right? And when we define the size, so size of type 1 error is alpha. Is the probability of committing type 1 error, that is alpha, and the size or the probability of committing type 2 error is beta. Okay, And here the power is actually 1 minus beta. Means probability of not committing type 2 error. Okay. So again, this is a thing to be considered. Now here, right, as we have the results, right? We are the so that is the contribution. Like this is the contribution of the location, high contribution, right? The type is having relatively low contribution, and as we have mentioned, that location, the interaction effect is insignificant. So if it has further low contribution. So as per the two main effect, location has higher amount of contribution to the explained variation, and the type is having a relatively low, and the interaction is having much lower uh, contribution to the uh, explained variation. Right? So these are the results as per the results that we have obtained, as per the p-value also. And related to the power, right, these are the power, the probability of not committing the type 2 error. So as you can see, the location has a substantially big value, reaching to 1. The type is having 0.557 low row value, and this is having a relatively much lower p-value, much lower the power. So these are the multiple comparison that we have discussed earlier also. So you can repeat this. So this is exactly the same as we have discussed in the case of ANOVA, one-way ANOVA, right? So we are not going with that. So this is related to, just a moment, related to two-way ANOVA that we discussed. Now, after that, I am taking one more analysis, right? That analysis was related to a non-parametric part, right? Like here, we have examined uh, for more than two category when the variable is metric in nature or y is metric in nature. Instead of this, we have one more thing that we can consider, the k independent test for proportion also, right? So for that, mm, we are taking up another test, that is the chi-square test of proportion. So here, uh, uh, so far in the ANOVA, what we examine? We examine k independent sample test for means. Right? Means with the hypothesis as mu1 equals to mu2 equals to mu3 equals to mu k, and k is greater than 2. And this is for ANOVA. In the same way, we can examine the another aspect, that is the k independent sample test for proportion, which is better known as chi-square test of proportion. Okay, with the hypothesis as P1 equals to P2 equals to P3 equals to Pk, where K is greater than 2 or greater than equals to 2. Okay, right? So here, this is the test that we are examining. It is also under non-parametric test when the normality assumption about the population cannot be made. So this is the chi-square test, that is a non-metric or categorical data at P1, P2, comparing proportion or equal presence of more than two categories. Okay. So here we will be using chi-square, with chi-square starts as summation OI minus EI whole square divided by AI. Okay. So here, with the condition that sum of observed frequencies should be equal to sum of expected frequency. Right? Remember, these OIs are the observed values that is there from the sample, observed frequencies from sample, and these EIs are the estimated frequency that comes under H naught, means they have equal presence. It means suppose we have 900 observations. So equal presence means each category would have the 300 observation for the three set, right? So this is the test that we are going to perform here, right? So this is the chi-square test of proportion that we are going to do here. Okay. So accordingly, uh, suppose we want to examine whether we have equal proportion for the four locations or not. So let me first propose the hypothesis, then we should compare, right? So here for this test, we are going to examine. So with the hypothesis as there is a equal presence, means P1 equals to P2 equals to P3 equals to P4, right? And this is for location, means there is an equal proportion of location in the data set, in the our category. So it can be written as proportion of northern equals to proportion of eastern is equal to proportion of western shore is equal to proportion of southern shore. And H1 is they are not all same. Right? So here we are going to apply the chi-square test of proportion for this situation. So now the SPSS sheet is there. Yes. We go to analyze. Since all the tools are available under analyze, then we go to the non-parametric part. Then we go to the legacy. And here we have chi-square test. So what is our path? Analyze to non-parametric to legacy dialog to the chi-square test. So this is a chi-square test. And here we have location of the outlet. Okay. And how the expected value we are having? All categories are equal. We are using the default option. Otherwise, you can put some values and add those values for these two categories. Right? So these are the expected range that we are going to use, expected values that we are going to use here. And then we press OK. So this is the output for the chi-square test. Right? Now at present, we have 11 outlets for the northern, right? 21 for the eastern, 23 for the western, and southern, we have 5, right? Now, since as per the expected frequency, right? Since we have taken the expected frequency as per the H naught. So we have 60 outlets total. And if we divide it by 4, so we will be having 15 frequencies or 15 values for each category. So here we have the expected value. This is 15, 15, 15. And these are the residuals, that is OI minus EI. This is chi-square statistics as we have discussed. The chi-square statistic is actually the sum of this. This is OI. OI is the observed value, right? Like for the northern, we have OI as 11 and EI as 15. So this is OI minus EI whole square. Then we divide it by EI. Here I is 4, 1 to 4, right? Now, if OIs and EIs are nearly same, right? So there will be having a low difference. So chi-square value would be low. So in that case, the observed frequencies and expected frequencies are same. It means all are having equal presence. And but if someone has a high presence, a one category is having high presence. So one of OI would be very high as compared to EI, and other OI would be relatively low as compared to EI. So in that case, we will be having large value of chi-square. If we have a large value of chi-square, right, then obviously p-value would be low, right? So this is a large value and this p-value is low. So this is less than 0.05. Less than 0.05 means we are rejecting H naught. Means there is not equal presence, right? Means some particular location dominate as far as the presence of the outlets are being considered. Okay, so now I am clearing this and I am going back to my whiteboard. Okay, so as we have discussed here the chi-square stats value, where the chi-square stat is sigma OI minus EI whole square divided by EI, with the condition that uh, sum of OIs equals to sum of EIs. Okay, and here chi-square stat is 14.4, and accordingly the p-value or significance is 0.002, which is less than 0.05. So we reject H naught at 5% level of significance. Means all locations are not having equal presence or equal proportion. Right? So this test is also in some way similar to the one-way ANOVA, but as far as practical point of view is concerned, but conceptually they are much different as we have discussed. So that's why we are covering this in that part where we are having more than two independent samples. Okay, so this is about uh, chi-square test of proportion. Okay. Thank you.